Hello. Thanks for coming, everyone. Um, I'll start now because we only have 50 minutes until the next talk starts, and then the next one. So we're tight on schedule. But first, thank you all for coming. I can't tell you how happy I am to see who I'm talking to. So let me tell you a little bit about myself. My name is Piet van Dongen. I work at Luminis. I am Dutch. I live in Arnhem nearby, and I am a cloud consultant. I'm helping organizations drive innovation using cloud technology. So I either advise them or implement stuff, or a combination of both. I work at Luminis, and we have a stand right around the corner here, where you can guess how heavy our cloud that we displayed is, and you can win some books and a super cool Lego Nintendo. But that's not why you're here. You're here because I want to talk about resilience engineering. So, what will you learn in the next 12 minutes? So this is a talk about resilience engineering. So we'll start off with resilience. And I'm going to explain what resilience is exactly. So this will give you an idea of what resilience is and what it is not. And then the engineering part comes into play. I'll talk about what? Still works? Great. I'll talk about the safety science, systems thinking, and the socio-technical system. And then finally, I'll give you some pointers so you can do a resilience engineering deep dive yourselves. All right, so now, what is resilience? To understand resilience, you need to think about robustness first. So we, software people, are really good at building robust systems. Systems that are highly available, that can handle a little peak load and a little stress. And to do so, we use techniques like redundancy, fallbacks, retries, failovers. Sound familiar? Well, it's quite busy. You can sit on the stairs if you. Okay. And we tend to build robust systems because we tend to think about what might go wrong. So servers might fail, or networks become unreliable, or services go down. And because that's what we focus on, that's how we design our systems. And that sounds wise, but it's actually doing ourselves a disservice. Let me explain why. So, as I said, we design around the things we know can go wrong. And resilience engineering people sometimes call these things that we know can go wrong the known unknowns. And if you want to defend yourselves against known unknowns, you end up with a robust system. And that's nice, robustness. But robustness does not protect us when things go south in the most unexpected ways. If you have a retro encabulator that has a hydrocoptic Marshall vane that goes from horizontal to vertical, robustness and redundancy are not going to help because you couldn't anticipate that would happen. And that's what we call unknown unknowns. Like black swans, we thought they wouldn't exist until some people sailed to Australia and encountered them. So that's the stuff that resilient systems can handle and robust systems cannot. So take this castle, for example. It's really hard to get inside a castle if you don't have an appointment, and especially if you're considered an enemy. It has a moat, thick walls, small windows, and at wartime it's lined with defenses like boiling oil and arrow-shooting knights and cannons, that stuff. So it's robust, but it's not resilient. If I would throw a bomb on a castle from a fighter jet or something, it would break. Or if I had mustard gas and helicopters, these thick walls and this moat wouldn't help. So a castle is designed to withstand what we know can go wrong. So it's robust. So castle engineers, or whatever they are called, designed for robustness. They made sure the chance of penetration was very small on their tech. An unknown known, no, a known unknown is a secret, something that you don't know but still exists. An unknown known is an intuition, something you get but can't articulate. But an unknown unknown is something totally unexpected and unforeseen, something you can design for, like F-16s and mustard gas in the year 500. So defending against unknown unknowns might seem impossible, and it is in a sense, but the good news is that resilience engineering helps you cope with unknown unknowns. So let's have a look at a resilience system now, something we all have, our bodies. So the human body, or any body for that matter, is an excellent example of a resilient system. So you are wired to prevent accidents from happening, and your nervous system, for example, is much faster than your conscience. So every time you do something, your body is learning. Especially when you almost get into an incident, like a near miss with another car, you subconsciously get better at preventing accidents by practicing. And if an accident does happen, like, for example, falling from your bicycle on the way to the hospital and breaking your arm, like I may have done or may not have done a few years ago, your body still works. Not completely, it hurts, but it still functions. And after a few weeks, broken bones and bruises and concussions, they are healed, and they repair themselves, and you're less likely to hurt yourself in the same way again. So I haven't fallen from a bike since then, and it probably won't happen again. So that's what resilience engineering is all about, being able to handle accidents and learn from incidents. Okay, so now I've explained the difference between robust and resilient systems, and now we'll dive into the engineering part of resilience engineering. Okay, so let's go back to my example about known unknowns, the things we know can go wrong. So like I said, if you think about these things, you tend to focus on preventing error. And how do we do that in engineering? By minimizing variance, writing a lot of documentation. For example, a Boeing 747 flight crew operating manual is 4,000 pages long. And by enforcing things, like making it impossible to shift into reverse while driving your car. And that's all cool, but that only helps us prevent the known unknowns. And there are a lot more unknown unknowns. Okay, anybody seen the HBO series Chernobyl? If not, you must have heard about the incident or the accident, the disaster in Chernobyl. And although that's quite awful and shocking, it's a good framework for explaining resilience engineering, because it is a good example of a disaster caused by unknown unknowns. For example, the reactor core's control rods had graphite tips, which set off a chain reaction that caused the explosion. Nobody anticipated that. There was bad management and top-down pressure that caused all sorts of minor errors and eventually led to a huge disaster. And in the aftermath of the disaster, critical information was covered up by people in powerful positions, making the aftermath worse than it could have been, just to name a few. So how do you deal with these things you couldn't beforehand predict? And that's what the field of safety science is all about. That's the birthplace of resilience engineering. And in trying to create a safer world, safety scientists are trying to shift the focus away from avoiding things that can go wrong sometimes to making sure things go right most of the time. And they don't do this by just focusing on technology, but on humans as well. So when resilience engineering advocates talk about systems, they don't mean components or computers or networks. They are talking about the so-called socio-technical system. Socio as in the people that interact with the technology, like this man here, and technical as in the technology that people and components interact with. And this perspective, this way of thinking about hundreds or dozens or thousands of parts that interact with feedback loops and input-output stock, is known as systems thinking. And whether you like it or not, humans are always part of the systems we create. So the Chernobyl example again, the system. What was the system there? Was it the power plant, the control room, the reactor, the steam turbines, the fuel, or the people as well? The operators, the managers, the government, the engineers, the firemen, or all of them together? And if you think in socio-technical systems, then the answer is all of them together, the humans and the technique. So, how do you prevent error then? So, what do you engineer to get resilience? Because you can create systems, but you cannot create humans. And that's where the engineering part of resilience engineering finally comes into play. So when things go wrong, they don't go wrong suddenly and all at once. Again, Chernobyl, the explosion was the climax, but what caused it? The operators in the control room pressing a shutdown button? Maybe. but they did not anticipate an explosion. And they didn't even completely understand what was happening at the time, even though the control room was full of data for them. And they were under a lot of pressure by superiors, who were under pressure themselves as well. So nobody imagined that an explosion would happen, and that means that the state of the system that people imagined in their heads was radically different from what was the actual state of the system. So, as you see, a lot of factors are at play, human and technical factors, socio-technical, and that's a central theme of resilience engineering. So to make sure things go right most of the time, we have to use the engineering skills we have. And how do we do it? Do that by helping the human part of our systems as much as possible. For example, one way to do that is to create transparent systems. Systems that can tell you what's happening at any point in time. So if you press a button, you immediately get feedback on what the new state of the system is. And that way, you can imagine the state of the system as close as possible as to the actual state. Another way is to do the equivalent of fire drills. So chaos engineering, for example, does this automatically and continuously by breaking down parts of the system, triggering a response, and that leads to an increase in resilience in the socio-technical system. So the next time something goes awry, you will be better prepared. And lastly, when things go wrong, and they will go wrong always and all the time, you have to keep an open mind. So don't focus on finding a single root cause, because a single root cause doesn't exist. And if you focus on a root cause, it only limits your chances of success the next time, because you will be focused on one thing and not the whole. Don't blame each other, because you have to realize that the moment of disaster is the best opportunity to get better the next time. So you have a learning opportunity there. And then you can create a system that increases the chance of success over time. And that's what resilience engineering is all about. So in conclusion, resilience is not robustness. Resilience engineering is about creating success, not about eliminating error. And it is about humans as much as it is about technology. It's about successfully controlling the complex system that they formed together. So thank you for listening. I hope you've learned something today. If you want to learn more, you can go to a blog post I wrote with some pointers. You can come talk to me at our stand between room 7 and 9. You can win some books about resilience engineering there if you guess the weight of our cloud we installed there. And if you have the most correct answer, you could win a Lego Nintendo. There's nothing to do with resilience, but it's still fun. Okay, thank you very much. We have time, 1.5 minutes for questions while the next one sets up. If anyone has one, and otherwise you can come to me afterwards.